I wish I brought my laptop.
Can you move those papers so we could see the computer screen from that?
That's the accelerating voltage, but everybody knows that. That's what attracts the electrons down the column. This, what's this? It's a lens. And what's this particular lens doing? It's condensing the beam to a spot. So what's the name of this lens?
Condenser.
It's a condenser lens. Finally got one right. Okay. So this rod here,
Aperture.
those are the apertures. This red thing, it's related to this.
What's the aperture, sorry? The one
This rod. Yeah, but you knew that. So,
Yeah.
And this thing here, that's related to this letter,
The scanner.
those are the scan coils.
Scan points.
Coils.
Coils.
Or deflector coils.
Or diflector.
And this thing down here, any particular one? You can only pull that one once.
Uncondensing.
That's how I feel when I'm grading exams.
Is that the name of the lens or how you feel? No, it doesn't matter.
Maybe a comedy video.
Subjective lens,
Objective.
which is also a condenser lens, but they usually don't refer it as another condenser lens. It's what's the function of this lens? Pardon?
An objective one, sorry.
Yep. If that'll help you.
To show the object?
This is the object down here.
Be to
So
magnify.
What's the focus?
it's the one that's going to take the electron beam and focus it at the correct distance, so that if your sample's at that distance, your object will be in focus.
So focus is being at correct distance.
No, it focuses the beam at a distance.
Which may or may not be correct.
That's right. If your sample's there, then that's probably correct. If it's not there, then you may need to move the sample up to, so that's how you can set your working distance, and the sample has to be moved. What's the difference between the Z and the working distance?
The working distance is the distance from the sample to the beam, and the Z distance is... Oh, no. The working distance is the distance of focus from the sample to the beam, and the Z distance is like the literal distance. Maybe I'm confusing them, or maybe I'm making it up, but I thought that was right.
That's close. The working distance is the distance the lens works at. Here's your little mnemonic. So working distance is the distance the lens works at, and what does the lens do? It focuses. So it's the distance that the lens is going to focus it at. If your sample happens to be there, then it's in focus. Z is the vertical distance in position of the sample. If the working distance is equal to the Z distance, then what event happens?
Focus?
You're in focus.
Yeah.
That's right. You keep tossing out enough words, you're bound to get one of them right. Let's go on to the next. All
I
right.
knew that one. Remember we spent like half an hour on that one?
Doing your practical.
Yeah.
Okay. And what's this thing? What's this thing here?
Faraday.
That's your Faraday cage and the scintillator and all the other parts of it. So here's STEM. So this is where you're in scanning mode, but you're passing through a slice of a sample. So it's a combination of scanning and transmission.
Is that similar?
Say that again? So
STEM, scanning, transmission, EM. So you're transmitting through a sample, but you're doing it, it's not in one giant spot the way a normal TEM operates, but rather one dot at a time.
Oh, okay. And what's the advantage of doing that?
I'm glad you asked. That allows you to do chemical analysis,
Okay.
so that if you have a cross-section of the cell, you don't have to magnify it so that all you see is a vesicle. You can have it at a lower mag, and as you're scanning, you're collecting X-ray data a dot at a time.
Oh, okay.
So a STEM tends to be material science people, And we have a STEM attachment here, which I demonstrated for you. All right, so difference between the raster pattern and a flood beam. The flood beam's all at once, and the raster pattern is a dot at a time. Resolution, you should be able to define it. And you can see the difference in the standards. So this is gold particles on carbon, and you're looking for this, the smallest distance you can measure. So our software takes all the different distances it can measure and it averages them and looks for it. So it's not exactly the same thing as measuring a few of these to get the smallest distance you can find. This is a crystal mounted on a grid, so this spacing is known what that spacing is. So if you can visualize it, then you're being able to see that line spacing. All right, so here's your resolution rule of thumb. Here's your Monte Carlo. These are the different signals produced. So we're talking about make sure you can identify what the Nyquist sampling rule is. You have to hit your sample with 2 to 3 dots in order to visualize it. More dots doesn't give you better resolution. So it's something like this. These big spots wouldn't show any difference in gray because they would all be averaged together. So this would just appear as a gray spot, so you wouldn't see these little things sticking up. If you make the dot smaller, then as you scan it across these smaller objects, then you wouldn't be summing up the values to gray, and you would see a difference in intensity to tell you there was something there. So magnification has an effect if you keep your spot size the same. All right, so you need some grids to stain.
So is everyone keeping that?
I gotta figure something out. Okay.
Is that your account?
No.
Yeah, this is dedicated. Dedicated cat owner.
Are these online? Does anyone know?
Yes, it is.
they're online.
Oh, they are? Where? Like Blackboard or on the one website that has?
Blackboard.
Didn't he only get through half of these the first time?
Like, how do you do that the first time around? Just like,
Because
one
one
was
was this
understood.
do you guys understand it before?
Do you understand it now?
No, but it's just helping that it's going faster. It just can't go against months, not like going less than 3 hours.
I mean,
I think
we're
this
only
might
like
last
15
it.
minutes in and you don't know what the next 2 hours and 45 minutes are going to be like.
We're only 10% done. Just as a heads up for
But
everyone.
you said you didn't go through all of the questions.
Yeah, didn't he say he was going to go through the second half
Oh,
next
where'd
time?
mouse go?
Somebody having coffee?
Yeah, there's one right here. It's his. Dude.
We're moment, man.
It's like Irish coffee.
Do it.
I wouldn't doubt it.
He comes in and you're drinking his coffee. So great.
Sitting in his chair.
Teaching the class.
Teaching the class. We're all taking notes.
This is a microscope, pretty straightforward. Let's move on.
Do it. No way.
So this would be a written exam and a practical for scope.
Yeah.
Oh yeah. We're gonna know how to use this thing by the end of the class, I feel.
Yeah. Let's hope.
That was the point, I guess.
I have to start coming
That
here
wasn't the point for me. I was like too
more
easy
often.
in it.
Was it me too?
It was like, how can I finish my cell molecular bio major with 2 units? I know, I'll take this easy fucking lab.
Yep, that's what I thought too. I needed 1 unit to graduate, and I was like, oh, 2 units will more than suffice. I'm not taking that 2 unit class. It's like, microscope class.
How hard can it
Okay,
be?
yeah. Yeah.
Just reminds me of 366, like, okay, just scan it over and take a picture. Life is so easy, I could do pictures all day, I'll definitely take that class.
Gee, you didn't go ahead.
We did, but then we went back for a review for Inchazar.
Whatever.
Alright, so vacuum systems, why we need a vacuum, these are all pretty straightforward. So the pumps don't work by themselves. So the ones above can work by themselves, but they don't all go to high vacuum. The ones down below work in conjunction with other pumps.
Sorry, can you tell us what, why do we need a vacuum?
That's right, it's on Blackboard.
But would it still work without a vacuum?
Yes.
Cause, yeah,
But
because
you have to have a weak vacuum.
from what I see, it says like it makes things better, but
Well, you just can't make much of a beam if you're in atmosphere. That's why. So when you go into that leaky vacuum mode, the low vacuum mode, you're bleeding air into the chamber, so your vacuum's not as good.
oh, okay.
But it introduces other problems. All right, so these are all levels of vacuum. These are how different gauges, how they work.
So, yeah, I just ran out of space on my phone.
All right. So any of these diagrams are reasonably good. All right, different kinds of ways to emit electrons. Here's the gun. Here's the anode plate, tungsten tips. We have a field emission source here. So that's different from simply having a bent wire that you heat up. All right, so different operation of the two. The SEM's a spot by spot and the TEM's a wide beam. So how do we control it? We make lenses. So we make a tube with wire wrapped around it. So more wire makes a stronger field, more current, more metal. All of these contribute it. But when you start doing that, it starts heating it, so you have to put cooling coils in it. So that starts making things more complicated. And the pole piece simply concentrates where the field is, and so if you reduce it from being this large a field to this very small field in the center, you've concentrated it into a smaller area, makes it more powerful. Alright, so these are the different aberrations. So we don't have colors in the electron microscope, but we do have differences in wavelengths. So those need to be corrected. Everyone's familiar with astigmatism from hours of working on the scope. Spherical aberration was the Hubble telescope. Apertures cause differences in depth of field. As you get a smaller aperture, it reduces your electron dosage on your sample.
I learned it from lab.
Sorry?
The lab that we did?
You learned something from it?
Yeah.
I'm glad.
You should give her some of your coffee.
It's not coffee, it's tea.
What kind?
Good Earth. Alright, so here's your column configuration. We've already been through this. So your condenser 3 is also called the objective lens. Alright, so we've been over the Faraday cage, so you can all reproduce that.
Like literally draw it?
Yes, like literally draw it if I asked you to.
Can you go back to that? Sorry.
It has something to attract the electrons.
Takes physics 196. Becomes a lot easier.
It
You
contains.
don't have to. 180 and 180B.
Alright, anything else about it?
So the Faraday cage is, sorry, this, so this is a secondary collector, and
Right.
then this is a Faraday cage right here, just that right there, these things.
Well, that whole cage there is charged,
So this is, the whole cage is the Faraday cage,
right?
even this?
Yeah.
Okay. What is the function of the Faraday cage?
It's positively charged. What's the charge on an electron?
Negative.
So what's going to happen?
Neutralize.
It's going to attract them. So they're accelerated into the detector where they're converted from electrons to photons, and then the photons go into a photon amplifier or a multiplier, and that then gets sent off to your view screen. What's the difference between the collection in the difference between collection in the secondary electron detector compared to the X-ray detector?
Speed of the electrons are hitting it.
Or the backscatter detector?
Can you repeat the question?
What's the difference in the collection abilities of the secondary electron detector compared to the X-ray or the backscatter?
The secondary attracts the electrons to it. Like the backscatter just gets the ones that are off the sample, go directly to it.
Right, it's line of sight. So it's not on a direct line from your source to your detector. It doesn't get captured. So you can't attract the X-ray photons and you can't attract the backscatters.
Do all secondary electron collectors have the Faraday cage?
Yes. No. No, because when you work at your low vacuum, this is the secondary electron detector here, this little tab here, and it doesn't have a charge on it.
Mm.
Okay. All right, so backscatters, as you know from your Monte Carlo, come from deeper within the samples, so this is a silver label inside of the cells. You can image it because your Monte Carlo goes deep enough into the cells that you're picking up backscatters from the silver, whereas you can't see anything on the surface. You can sort of make out the little fried egg look, those are the nuclei. But to really say for sure, you can label the nuclei with silver. All right, and these are just gold particles on the surface. This is your backscatter of a rock. And the different atomic weights cause different numbers of backscatters to be generated, so that's why you have different intensities there of the rocks. In a secondary, this would all look like a uniform gray. All right, so some of the specialized types of things you can measure. You hook up a meter, you can measure the electrical current from the beam into the sample and then going through the sample off to a detector. In this case, just a meter. The first detectors on the SEM were just specimen current. Auger are from the very, very close to the surface. They're similar to the X-ray photons. They give some compositional information, as do X-rays. Secondary electrons are mostly morphology, and your backscatters will give you a little morphology. Cl is for specialized rocks and other compounds that glow when they're illuminated with electrons.
Like what?
Like zircons. Geologists use that a lot, the Cl detector.
Fluorides.
All right, so everyone's familiar with what, can you get a secondary electron created here, where the cursor is?
Nope.
No.
Why not?
That little diagram, it's Monte Carlo, and it goes down to that little line.
No, that line shows you where secondary electrons that are created that can be captured by the secondary electron detector.
Okay.
This part down here, remember this is a sum of all the different distributions of electrons. So if you get an electron that's coming down in here, how does it create an X-ray down here? How are X-rays created?
By electrons moving from one shell to another.
And why would they want to move from one shell to another?
Because the electrons were displaced.
By?
Collision
Of?
Energy.
of electrons
From?
from the beam.
from the beam. So therefore you can have a collision taking place down here. I'm sorry?
So
We have to go through, we have to hopscotch through that again?
I
X-rays
don't want
move,
hopscotch, I just want
X-rays
like
move from one
tool.
shell to another due to electron collisions from electrons in the beam.
Okay, I'll get that later.
Okay.
So up here, when the collision takes place, up near the surface, then there's enough energy in those electrons to exit the sample if they're pointed that way. If they're pointed down, then they'll go down into the sample and then they will just be absorbed. And in being absorbed, they would then be part of the flow of electrons through the sample, which you would pick up in your specimen current meter.
But not in your secondary?
No, because they didn't exit the sample.
Okay.
So it
But
only
that
is,
was your question, right? Where the white space was?
could you have a secondary electron generated there? And the answer is yes. Would you pick it up in the secondary detector? The answer is no.
Okay.
You would pick it up in your absorbed current detector. So this is the problem with this diagram, is people look at it and they think that you can only create secondaries in this little black area, or in, I guess in the stipple, up and down stipple. But they can take place anywhere in the volume. They just can't be detected by that particular detector. So you can get backscatters that are down, deep down inside, but they don't exit the sample. Alright, so you can go through these different detectors and how they work and generating X-rays and all that great stuff. This is the way you display X-ray data between spectrum plots, plotting on the x-axis the energy versus the number of counts of X-ray photons. And an X-ray map here is showing you bright spots at every spot in the raster pattern where a particular element was present, and you get to select what elemental windows you want. You can have as few or as many as the program will allow. So here's your absorbed current. In this case, the circuit continues out here, but because there's a break in it right there, there's any current that comes down from the beam and hits this part of the circuit goes up to the break and can't cross the gap, so it doesn't get measured in your absorbed current meter. That's why it's not bright. So this area out here is being bombarded with beam electrons. They're not being absorbed much, so they don't show up as a bright spot. But in here, anything that hits the circuit gets carried away through to ground, and that goes out to your current meter. All right, here's your CL looking at zircons, a boyfriend's best friend. And so these different colors represent different ages of the rocks, and geologists just go crazy for that kind of stuff, because it allows them to figure out where this zircon came from, and they can trace it back up from the alluvial plain at the base of the river back up to what river draining into that gave rise to it. All right, so just a warning that your resolution in the SEM is based not on the incoming spot, but rather on the exiting spot. So your spots get progressively bigger. So your secondary is going to be smaller and therefore better resolution than your backscatter, which is going to be smaller and better resolution than your X-ray. All right, so this is effect of elements. So this is low Z and high Z. Those would be atomic weights. So as you go from a light element here to a heavy element here for the same accelerating voltage, the Monte Carlo gets a lot smaller because there's not as much power to drive into that heavier metal or material. At low Z and high accelerating voltage, then it's going to penetrate deeply, but as the element gets heavier, then the Monte Carlo gets smaller. As your penetration depth increases with increasing accelerating voltage, your Monte Carlo gets bigger, which means that what would be an acceptable Monte Carlo at lower accelerating voltage starts having overlaps at higher accelerating voltages, which means that it would affect your resolution.
Say it means that it wouldn't affect resolution?
It could,
No.
because you start getting overlaps, because remember your spot size is getting bigger and bigger as the Monte Carlo gets bigger. All right, so viewing uncoded samples, we can lower the KV to reduce the amount of current hitting it so you don't get the buildup of charge on it. This would be a sample that's not conductive. You can also neutralize the charge on the sample surface. One way to deal with the charge on the surface is to coat it. If you're dealing with museum samples, they frown on you putting a coating on a rare specimen. So, conventional SEM, you're going to look at high vacuum. It's got to be dry, or it's got to be frozen, because frozen is dry, because your liquid is basically bound up as a crystal. Charging is minimized by coating the sample or lowering the KV. In the variable pressure, you're going to neutralize the charge by ionizing gas molecules in the chamber. Rather than removing all of them, you're going to leave some in there. When you have your beam coming through, the gas molecules get ionized. The negative charge on the surface is neutralized by the ions created by the ionization of those gas particles, gas molecules. So you can figure out, you can answer some of these questions. The detectors that are used are backscatter detectors or special secondaries. So this is the trick. So at your gun, your field emission gun up here, it's at 10 to the minus 4 PA. But down here, your specimen chamber is at a much worse vacuum. And so you have apertures in here that prevent the gas from simply flowing evenly all through the chambers. And so that's how you can have high vacuum at one end of the scope and low vacuum at the other without messing things up too much. So you can read through some of this where the gas molecules are going to neutralize at the surface, and then you're going to generate secondary electrons that are going to be picked up by your variable pressure detector. I'm not so interested that you know the fine theory of this, just the basic idea that by bleeding in these gas molecules that are ionized, you then neutralize the charge on the surface. Alright, so here's bacteria and whatnot imaged wet on a rock, a live centipede, and this is water. You can't see this detail because the beam doesn't penetrate through water. So it's a gee whiz demonstration for you. Alright, any questions? You can raise those to me over the next 2 weeks before the exam. Alright, so we can take a short break and then I'll put up the other major slideshow, and that was specimen prep.